In mathematics, a finite field or Galois field is a field that contains a finite number of elements. As with any field, a finite field is a set on which the operations of multiplication, addition, subtraction and division are defined and satisfy certain basic rules. The most common examples of finite fields are given by the integers mod p when p is a prime number. The number of elements of a finite field is called its order. A finite field of order q exists if and only if the order q is a prime power pk. All fields of a given order are isomorphic. In a field of order pk, adding p copies of any element always results in 0, that is, the characteristic of the field is p. In a finite field of order q, the polynomial xq minus x has all q elements of the finite field as roots. The non-zero elements of a finite field form a multiplicative group. This group is cyclic, so all non-zero elements can be expressed as powers of a single element called a primitive element of the field A field has, by definition, a commutative multiplication operation. A more general algebraic structure that satisfies all the other axioms of a field but isn't required to have a commutative multiplication is called the division ring. A finite division ring is a finite field by Wedderburn's little theorem. This result shows that the finiteness condition in the definition of a finite field can have algebraic consequences. Finite fields are fundamental in a number of areas of mathematics and computer science, including number theory, algebraic geometry, Galois theory, finite geometry, cryptography and coding theory. Definitions, first examples, and basic properties. A finite field is a finite set on which the four operations multiplication, addition, subtraction and division are defined, satisfying the rules of arithmetic known as the field axioms. The simplest examples of finite fields are the prime fields. For each prime number p, the field gf of order p is easily constructed as the integers modulo p. The elements of a prime field may be represented by integers in the range 0, p-1. The sum, the difference and the product are computed by taking the remainder by p of the integer result. The multiplicative inverse of an element may be computed by using the extended Euclidean algorithm. Let f be a finite field. For any element x in f and any integer n, let us denote by nx the sum of n copies of x. The least positive n such that n1 equals 0 must exist and is prime. It is called the characteristic of the field. If the characteristic of f is p, the operation makes f a GF vector space. It follows that the number of elements of f is Pn. For every prime number p and every positive integer n, there are finite fields of order Pn, and all these fields are isomorphic. One may therefore identify all fields of order Pn, which are therefore unambiguously denoted Fpn or Gf, where the letters Gf stand for Galois field. The identity is true in a field of characteristic p. For every element x in the prime field Gf, one has xp equals x by applying the above identity to x and 1, where x successively takes the values 1, 2, p-1 modulo p. This implies the equality for polynomials over Gf. More generally, every element in Gf satisfies the polynomial equation xpn minus x equals 0. Any finite field extension of a finite field is separable and simple. That is, if E is a finite field and F is a subfield of E, then E is obtained from F by adjoining a single element whose minimal polynomial is separable. To use a jargon, finite fields are perfect existence and uniqueness. Let Q equals Pn be a prime power, and F be the splitting field of the polynomial over the prime field Gf. This means that F is a finite field of lowest order, in which P has Q distinct roots. Above identity shows that the sum and the product of two roots of P are roots of P, as well as the multiplicative inverse of a root of P. In other words, the roots of P form a field of order Q, which is equal to F by the minimality of the splitting field. The uniqueness up to isomorphism of splitting fields implies thus that all fields of order Q are isomorphic. In summary, we have the following classification theorem, first proved in 1893 by E. H. Moore. The order of a finite field is a prime power. For every prime power Q there are fields of order Q, and they are all isomorphic. In these fields, every element satisfies and the polynomial factors, as it follows that GF contains a subfield isomorphic to GF if and only if M is a divisor of N. In that case, this subfield is unique. In fact, the polynomial divides if and only if M is a divisor of N. Explicit construction of finite fields. Non-prime fields given a prime power Q equals Pn with P prime and N greater than 1, the field GF may be explicitly constructed in the following way. One chooses first an irreducible polynomial P in GF x of degree n, then the quotient ring of the polynomial ring GF x by the ideal generated by P as a field of order Q. More explicitly, the elements of GF are the polynomials over GF whose degree is strictly less than n. The addition and the subtraction are those of polynomials over GF. The product of two elements is the remainder of the Euclidean division by P of the product in GF x. The multiplicative inverse of a non-zero element may be computed with the extended Euclidean algorithm. See extended Euclidean algorithm. Simple algebraic field extensions. Except in the construction of GF, there are several possible choices for P, which produce isomorphic results. To simplify the Euclidean division, for P one commonly chooses polynomials of the form which make the needed Euclidean divisions very efficient. However, for some fields, typically in characteristic 2, irreducible polynomials of the form may not exist. In characteristic 2, if the polynomial xn plus x plus 1 is reducible, it is recommended to choose xn plus xk plus 1 with the lowest possible k that makes the polynomial irreducible. If all these trinomials are reducible, one chooses pentanomials xn plus xa plus xb plus xc plus 1 as polynomials of degree greater than 1, with an even number of terms, and never irreducible in characteristic 2, having 1 as a root. In the next sections, we will show how this general construction method works for small finite fields. Field with 4 elements over GF, there is only one irreducible polynomial of degree 2. Therefore, for GF the construction of the preceding section must involve this polynomial, and if one denotes, say, a root of this polynomial in GF, the tables of the operations in GF are the following. There is no table for subtraction, as, in every field of characteristic 2, subtraction is identical to addition. In the third table, for the division of x by y, x must be read on the left, and y on the top. GF for an odd prime P. For applying the above general construction of finite fields in the case of GF, one has to find an irreducible polynomial of degree 2. For P equals 2, this has been done in the preceding section. If P is an odd prime, there are always irreducible polynomials of the form x2 minus r, with r in GF. More precisely, the polynomial x2 minus r is irreducible over GF if and only if r is a quadratic non-residue modulo P. There are quadratic non-residues modulo P. For example, 2 is a quadratic non-residue for P equals 3, 5, 11, 13, and 3 is a quadratic non-residue for P equals 5, 7, 17. If P3 mod 4, that is P equals 3, 7, 11, 19, one may choose -1 P-1 as a quadratic non-residue, which allows us to have a very simple irreducible polynomial x2 plus 1. Having chosen a quadratic non-residue r, let alpha be a symbolic square root of r, that is a symbol which has the property alpha 2 equals r. In the same way as the complex number I is a symbolic square root of -1, then, the elements of GF are all the linear expressions with A and B in GF. The operations on GF are defined as follows, represented by Latin letters are the operations in GF. GF and GF. The polynomial is irreducible over GF and GF, that is, it is irreducible modulo 2 and 3 nor in GF. It follows that the elements of GF and GF may be represented by expressions where A, B, C are elements of GF or GF, and is a symbol such that the addition, additive inverse and multiplication on GF and GF may thus be defined as follows, in following formulas. The operations between elements of GF or GF, represented by Latin letters, are the operations in GF or GF, respectively. GF. The polynomial is irreducible over GF, that is, it is irreducible modulo 2. It follows that the elements of GF may be represented by expressions where A, B, C, D are either 0 or 1, and is a symbol such that as the characteristic of GF is 2, each element is its additive inverse in GF. The addition and multiplication on GF may be defined as follows, in following formulas. The operations between elements of GF, represented by Latin letters, are the operations in GF. Multiplicative structure. The set of non-zero elements in GF is an abelian group under the multiplication of order Q1. By Lagrange's theorem, there exists a divisor K of Q1 such that xk equals 1 for every non-zero x in GF. As the equation xk equals 1 has at most k solutions in any field, Q1 is the lowest possible value for k. The structure or theorem of finite abelian groups implies that this multiplicative group is cyclic, that all non-zero elements are powers of single element. In summary, the multiplicative group of the non-zero elements in GF is cyclic, and there exists an element A, such that the Q1 non-zero elements of GF are A, A2, AQ-2, AQ-1 equals 1. Such an element A is called a primitive element, unless Q equals 2, 3. The primitive element is not unique. The number of primitive elements is phi, where phi is Euler's totient function. Above result implies that xq equals x for every x in GF. The particular case where q is prime is Fermat's little theorem. Discrete logarithm. If A is a primitive element in GF, then for any non-zero element x in F, there is a unique integer n with 0 nq-2 such that x equals n. This integer n is called the discrete logarithm of x to the base a. While the computation of n is rather easy, by using, for example, exponentiation by squaring, the reciprocal operation, the computation of the discrete logarithm is difficult. This has been used in various cryptographic protocols. See discrete logarithm for details. When the non-zero elements of GF are represented by their discrete logarithms, multiplication and division are easy, as they reduce to addition and subtraction modulo Q1. However, addition amounts to computing the discrete logarithm of n plus n. The identity n plus n equals n allows one to solve this problem by constructing the table of the discrete logarithms of n plus 1, called X logarithms. For n equals 0, q-2. X logarithms are useful for large computations, such as linear algebra over medium-sized fields, that is, fields that are sufficiently large for making natural algorithms inefficient, but not too large, as one has to pre-compute a table of the same size as the order of the field. Roots of unity. Every non-zero element of a finite field is a root of unity, as xq-1 equals 1 for every non-zero element of GF. If n is a positive integer, an nth primitive root of unity is a solution of the equation xn equals 1 that is not a solution of the equation xm equals 1 for any positive integer m less than n. If A is a nth primitive root of unity in a field F, then F contains all the n roots of unity, which are 1, A2, and -1. The field GF contains a nth primitive root of unity if and only if n is a divisor of Q-1. If n is a divisor of Q-1, then the number of primitive nth roots of unity in GF is phi. The number of nth roots of unity in GF is GCD. In a field of characteristic P, every th root of unity is also a nth root of unity. It follows that primitive th roots of unity never exist in a field of characteristic P. On the other hand, if n is coprime to P, the roots of the nth cyclotomic polynomial are distinct in every field of characteristic P. As this polynomial is a divisor of xn-1, which has 1 as formal derivative, it follows that the nth cyclotomic polynomial factors over GF into distinct irreducible polynomials that have all the same degree, say d, and that GF is the smallest field of characteristic P that contains the nth primitive roots of unity. Example: the field GF has several interesting properties that smaller fields do not share. Specifically, it has two subfields such that neither is a subfield of the other, not all generators are primitive elements, and the primitive elements are not all conjugate under the Galois group, the order of this field being 26, and the divisors of 6 being 1, 2, 3, 6. The subfields of GF are GF, GF equals GF, GF equals GF, and GF itself. As 2 and 3 are coprime, the intersection of GF and GF in GF is the prime field GF. The union of GF and GF has thus 10 elements. The remaining 54 elements of GF generate GF in the sense that no other subfield contains any of them. It follows that they are roots of irreducible polynomials of degree 6 over GF. This implies that, over GF, there are exactly 9 equals 54 sixths irreducible monic polynomials of degree 6. This may be verified by factoring x64 minus x over GF. The elements of GF are primitive nth roots of unity for some n dividing 63, as the third and the seventh roots of unity belong to GF and GF, respectively. The 54 generators are primitive nth roots of unity for some n in 9, 21, 63. Summing these numbers, one finds again 54 elements. By factoring the cyclotomic polynomials over GF, one finds that the 6 primitive ninth roots of unity are rootsive, and are all conjugate under the action of the Galois group. The 12 primitive 21st roots of unity are rootsive. They form 2 orbits under the action of the Galois group. As the two factors are reciprocal to each other, a root and its inverse do not belong to the same orbit. The 36 primitive elements of GF are the rootsive. They split into 6 orbits of 6 elements under the action of the Galois group. This shows that the best choice to construct GF is to define it as GF x. In fact, this generator is a primitive element, and this polynomial is the irreducible polynomial that produces the easiest Euclidean division. Frobenius automorphism and Galois theory. In this section, P is a prime number, and Q equals Pn is a power of P. In GF, the identity implies that the map is a GF linear endomorphism and a field automorphism of GF, which fixes every element of the subfield GF. It is called the Frobenius automorphism, after Ferdinand Georg Frobenius. Denoting by the composition of with itself, k times, we have it has been shown in the preceding section that is the identity. For 0 less than k less than n, the automorphism is not the identity, as, otherwise, the polynomial would have more than pk roots. There are no other GF automorphisms of GF. In other words, GF has exactly n GF automorphisms, which are in terms of Galois theory. This means that GF is a Galois extension of GF, which has a cyclic Galois group. The fact that the Frobenius map is surjective implies that every finite field is perfect. Polynomial factorization. If f is a finite field, a non-constant monic polynomial with coefficients in f is irreducible over f. If it is not, the product of two non-constant monic polynomials with coefficients in f. As every polynomial ring over a field is a unique factorization domain, every monic polynomial over a finite field may be factored in a unique way into a product of irreducible monic polynomials. There are efficient algorithms for testing polynomial irreducibility and factoring polynomials over finite field. They are a key step for factoring polynomials over the integers or the rational numbers. At least for this reason, every computer algebra system has functions for factoring polynomials over finite fields, or, at least, over finite prime fields. Irreducible polynomials of a given degree. The polynomial factors interlinear factors over a field of order Q. More precisely, this polynomial is the product of all monic polynomials of degree 1 over a field of order Q. This implies that, if Q equals Pn, that xq minus x is the product of all monic irreducible polynomials over Gf, whose degree divides n. In fact, if P is an irreducible factor over Gf of xq minus x, its degree divides n, as its splitting field is contained in Gf. Conversely, if P is an irreducible monic polynomial over Gf of degree d dividing n, it defines a field extension of degree d, which is contained in Gf, and all roots of P belong to Gf, and are roots of xq minus x. Thus P divides xq minus x. As xq minus x does not have any multiple factor, it is thus the product of all the irreducible monic polynomials that divide it. This property is used to compute the products of the irreducible factors of each degree of polynomials over Gf. See distinct degree factorization. Number of monic irreducible polynomials of a given degree over a finite field. The number n of monic irreducible polynomials of degree n over Gf is given by where mu is the Mobius function. This formula is almost a direct consequence of above property of xq minus x. By the above formula, the number of irreducible polynomials of degree n over Gf is n. A lower bound for n is 1. May easily deduce that, for every q and every n, there is at least one irreducible polynomial of degree n over Gf. This lower bound is sharp for q equals n equals 2.